In this lecture, we want to return to a more formal discussion of our state vectors, our quantum state, if you will. And we've introduced these notions already through some examples of our ket vectors, we call them. And they represent the quantum state for example, spin 1/2 and polarization problems. So here we're going to talk a little bit more generally about the nature of the space that these vectors live in, the vector space. And they live in what's called a linear vector space. And here we want to go through the definitions. We're not going to go through this in detail, but a lot of this should be familiar from your earlier studies of vector spaces and vectors. It should be clear. But what we want to do is consider some arbitrary vectors in a vector space V. And we also want to consider some arbitrary scalars that can be complex. This is the difference in quantum mechanics, is that the coefficients that we want to consider, the vectors, if you will, can be complex. So the formal way, which I did not include here, would be to say that we're considering a linear vector space where the field is the complex numbers. Okay, so let's look at these. First we have the vector addition axioms, how you add vectors and so on, and we have the following set. So addition is commutative, it's associative. We have an additive identity, which is just the zero vector. You can think of it as if it's all the zero entries for the elements of the vector. And it's the case that you add that to any vector, you get the same vector back for all vectors within that vector space. There's an additive inverse, which we can write as for any vector u, there's going to be a minus u, which again is just going to be the minus sign outside. We can take the minus sign outside in that case. But when we add those two vectors, it's zero. And again, just think back to your ordinary physics. If u is pointing in one direction, u is going to be pointing in the opposite direction, so they add up to zero. We also have scalar multiplication axioms. And so let's take a look at those. Again, we'll go through these quickly. And these are important. Some people kind of forget these, but you can distribute a scalar if you're multiplying by two vectors. You can distribute it. You can also do it the other way by distribute the scalars to a single vector like that. The multiplication is commutative, or if you will, so mu times the vector u is equal to times lambda is equal to lambda times u, mu, then times the vector u. Also note, the placement of the scalar can be in either side of the vector, though this is kind of more conventional form. It's just seen to be look cleaner, if you will. But you might see examples where that deviates a little bit. It's not a big deal. There's also the multiplicative identity. That's supposed to be identity. It's just one, of course. So you multiply by any vector, you get one back. And then there's some other relationships that are pretty straightforward. There would be the 0 times any vector is going to give you the 0 vector. Again, you can think of that as the vector with all 0 elements. If you take negative 0, it's equal to 0. So 0, again, negative 1 times 0 is 0. And again, double negation gives you back the vector. Okay, so hopefully these are pretty basic, but we just want to kind of emphasize these. And again, especially the distributive, that's one thing that a lot of people forget. Now, let's go on to other properties. We want to define linear independence, which is very similar. You've probably seen this before. It's just that given a set of vectors, they're linearly independent if the weighted sum of them is non-equal to 0 for non-trivial weights. And that just means that they're not all 0. Because, of course, if all the lambda are 0, then it's a trivial solution. So but this isn't the linear independent set is an important concept here as we go forward. Also, the span, we say a set of vectors spans the vector space if any vector v can be expressed as a linear combination of that. Now, these do not need to be linear independent. They can still span it, though. Well, that means we want to define what we call the basis, which is the case. We limit it to the independent set that spans the space. And again, here, we just want to think, again, go back to your basic physics and think about a three-dimensional space with your unit vectors. Your basis vectors are your unit vectors, I hat, j hat, k hat, for example. And they're orthogonal, they're linearly independent, and they span the space, and every vector can be written in three-dimensional space with those unit vectors. The number of basis elements defines the dimension of V, just like it would in the three-dimensional space case. So just draw back to your old case to draw analogies with what we need to do. What does change slightly is when we start considering the complex nature of these vectors, multiplying them, etc. So that's what we're going to do next, is define the inner product. Now again, as we did in relativity, this is just a generalization of the dot product, if you will. But so we're going to do it a slightly different way here. But again, here the metric is flat, so we're not going to be worried about like in general relativity, we're not going to have curved spaces or anything like that. And so the inner product will be close to the dot product, except with one slight change we need due to the complex nature. So again, we want to consider vectors and scalars like we did before. And we write the inner product as follows. So it's these two vectors, vector u and vector v. We will define more formally a little bit shortly the difference between these two. And that's an important thing. But right now we just want to define this inner product and its properties. And the inner product itself is a complex number. So again, just go back to your dot product of dotting two vectors together. Here we're dotting two vectors together. Though there is a subtle distinction, a distinction between these vectors pointing to the left and pointing to the right we need to make in a moment. But the product satisfies the same, which again is very similar to what we had for the dot product. It's distributive, and again, draw an analogy, go back to your ordinary dot product, and remember, does this work for that? Yes. So again, it distributes, so u times v plus w, we just draw that in. Scalar distributive, again, if we're taking this vector u, acting on this product here, the scalar just goes through any vector and operate. Whatever we do, the scalars can be moved around within a single term. Now, what's different here than the ordinary dot product is, which we'll prove in a moment once we get a little bit further into this, is that the ordering of those vectors matters. So if we take u acting on v, that's sometimes how we say it, or u on v, the inner product of u on v, and we take the complex conjugate of that, remember that takes I, the complex unit modulus, to minus I. What that does, it flips them around. So there is an order dependence here of these two vectors. Okay, what's important for us to tie to reality and why we're doing all this is embodied in the next one, or next two, is that when we take a vector and act on it with itself in this way, which again we do need to come back to the distinction between these two, but if we take the same vector in this way, what we get is a non-negative number, real number, non-negative, greater than 0 or equal to 0, and it's in the reals. And again, if the inner product of a vector on itself is 0, then that happens if and only if that vector, that's supposed to be a u, is 0. It's the 0 vector. And we define the norm, that's just the square root of the inner product, just like the dot product, remember? The dot product, if you take this square root of the dot product of a vector with itself, it gives you the length of that vector. Two further words which you might be familiar. So to define a normalized vector is one where the inner product with itself is equal to 1. This means it has unit length, if you will. And orthogonal vectors, u and v, perpendicular if you like, the inner product is 0. Very simple. And again, lastly, we have that for all vectors, if you act on it with a 0 vector in either way, you get 0. The scalar 0. Okay, so this defines a linear vector space and an inner product on that space. If we have both of those, we have what is called a Hilbert space. Now, there are more formal definitions of Hilbert space with more fine subtleties involved, but essentially for our purposes, this is what we need. So linear vector space with such an inner product defined as here, over the complex numbers. There are some theorems that you can break it into reals, but that just expands the size of the space because you can always represent complex number as two reals, but we won't consider that here. But this is our central result, is that the Hilbert space is the space in which our quantum state lives in, and we'll come back to that shortly. Now we want to come back and talk about a little bit the distinction between these two vectors, pointing to the left and pointing to the right. Now, they are separate in the sense that they live in separate vector spaces, and we call the other one, the new one, which is pointing to the left, it resides in what's called the dual vector space. It's a dual vector, or sometimes it's called the adjoint space. And we're just going to give it the V dagger. That will be clear shortly. Some people call it V with a tilde on top, but there's a close analogy between V and V dagger. Close connection, I should say. So now, as we probably stated earlier, these vectors that point to the right we call ket vectors, K-E-T. And for every ket vector, we call it, which is V, there's a unique bra vector. Now that's another term, bra vector, that points in the opposite direction but lies in this other vector space. So we can take products across those two, but they do lie in distinct vector spaces, so we can't add them. So it makes no sense to add this to that. And that's important to remember that. And the reason that this is called bracket, this is due to P.A.M. Dirac, that if you put them together like this, you get a bracket or a bracket. So he thought of these as a bracket, so kind of a cute notation. A bracket is our inner product. So that's kind of separating this two. Okay. So now we'll go through a little later and deal more with inner products and get practice with it. But for now, we just want to kind of do one more definition. The next one is an orthonormal basis. And all that means is we have a set of vectors that are mutually orthogonal and are normalized. So again, we had those definitions up here. They're all length 1 and they're mutually orthogonal. And we write this as follows, that the inner product of two of them, I'm using e's here to represent these. You can think of these as unit vectors. That's what the analogy is, or actually really what they are. Is that this is a Kronecker delta, which is equal to 1 if I is equal to j, it's equal to 0 if I is not equal to j. It's called the Kronecker delta. What we'll care about are a complete set, an orthonormal basis that's complete, which means it spans a space. So given that, we can expand vectors in this particular basis. And there'll be different bases, orthonormal bases, that we'll be considering. It's an important feature here. But when we have an orthonormal basis and a set of vectors, we can give our vectors in a matrix form. Not a matrix, but column and row vectors. That's what we mean. Column and row matrices, if you will. So let's take a look. So like we said, we can express any arbitrary vector in terms of our basis vectors, E, which are orthonormal, so that we would just have these coefficients, u11 up to un1 times en. Now, I'm using a notation here with double subscripts, so I'll be clear in a moment, because what we want to do is write these as matrices, where we write these as follows. Well, first of all, let's introduce our basis kets. Now, we can express our orthonormal basis kets as follows, as just say E1 is 1, all zeros, E2 is 0, 1, and all zeros. Clearly, these are going to be orthogonal, and clearly, they're normalized. There's only 1, 1 there. So that hopefully should be obvious. But what we would use here is the matrix notation here, where again, if we take the elements of, say, some matrix A, we say the element is A and M, where N refers to the row and M is a column. So it's always row column. Just remember that. And that allows us to express this matrix as such, where the diagonals always have the same. So this is row 1, column 2, and then there's row 2, column 1. Now we can express with these basis vectors this arbitrary vector u as follows. So this is why we use that double notation, because there's only one column here. So the second entry is always 1, but there are n rows. And this is another way to express it in this particular basis. Now here's where we got to remember, this column vector representation depends on the basis you're choosing. So it can change if you change bases. So it is basis dependent. Okay, let's move on and see how we get our bra vectors. So here again is our ket vector. Now the bra vectors are just row vectors. So here we see that the first entry is always 1 because there's one row and there's n columns, like that. And when we take the product, we see that we would just multiply these. We take v1 times u11 plus v12 times u21 and so on down the line. That's how we do our inner product. We'll just look at an example shortly. Okay, now the question is, given a vector, say u, how do we convert back and forth between the bra and the ket vectors and back and forth? Well, we're going to introduce something now that usually comes in a little later, but it's the mathematical process that we do, and it's called the Hermitian conjugate. Sometimes mathematicians say the word adjoint, but we're going to use Hermitian conjugate because we're physicists. And it's the relationship between the ket and the bra vectors. And again, we give it by the operation of dagger. Sort of like when we take a complex conjugate, we use a star. When we take a Hermitian conjugate, we take a dagger. And the Hermitian conjugate is sort of like the generalization of the complex conjugate to like matrices and row and column vectors. But let's take a look at what it does. So all it does is if you have a matrix and you look at its elements, we'll express this in different ways. So each element is A and M. Then the dagger, the Hermitian conjugate, that is, a dagger, sometimes we say, has elements A, M, N complex conjugated with a star. And notice what that does. All it does is it swaps rows and columns. And you take the complex conjugate of every element. We'll see the significant why this is important in a bit. We'll have a separate argument why that is. But just to think of it simply, all you do is you take a matrix, you flip it about the diagonal, it goes from upper left to lower right, and you take the complex conjugate of all the elements. And that's how you do your Hermitian conjugate. And that's how we can see we get from one to the other. And we'll take a look at an example in a minute. So let's take a look at our vectors. So here we have our u vector, which again, we're going to have elements u sub I1, because remember that it's a column vector, so there's one column, and there's I labels the row. And we want to take the dagger of that. So remember, we flip it and we take the complex conjugate, and that defines the bra vector. Because notice, if you flip it, this has one column, now this has one row. And that complex conjugate is critical. So that's something that a lot of people forget about, but it's important to remember to take that complex conjugate. So let's do an explicit example here. So let's say u dagger is this particular four-dimensional vector, 1i, 3 plus 2i, e to the minus I pi over x, and we're taking the Hermitian conjugate of that. So essentially what we do is we take it and we lay it on its side like this. So whatever the first column is now the first row is now the first column, etc. And we take the complex conjugate. So we 1 minus I, and then 3 minus 2i, and e to the I pi over 6. And that's our bra vector. And it should be clear that if I take the conjugate again of this bra vector, I'm going to get back that original u vector. So it just goes back and forth. Just like complex conjugation, remember. If you take a complex conjugation of a number, you do it again, you get the original complex number back. Okay? Now let's look at how we form the inner product, and let's do this in general. So let's say we have the two vectors, u and v, given by their elements. Notice now we're taking the crutch away of labeling the double subscripts, so we're just going to use these single subscripts now. And so when we go to the bra vector, should be clear what we're doing. But now what we do is we take, to form the inner product, we need to take v. We're going to do u on v. So we're going to take u, lay it on its side, take the complex conjugate, and then like this. So we just took this, laid it on its side, and took the complex conjugation of all the elements, and we have v1 here. And we carry that out, we simply get what you expect. u1 star v1 plus u2 star v2 plus all the way down to un star plus vn. And that's the inner product. And of course you can see, notice that if all the elements were real, this would be the same as our ordinary dot product. So it's just this complex conjugation that's important that we got to remember. Okay, so there's some details of how we go about this. And with this now, with this kind of a little bit more formal coverage of this, let's restate our first postulate, but in a more appropriate manner now with our Hilbert space. So, we say now that the quantum state of the system is represented mathematically by a normalized vector psi in a Hilbert space H. And we'll go into the reasons behind that, basically related to probability, why it needs to be normalized. The quantum state contains all the information that can be known about the system, which is what we said before. Okay. Now, the other thing, important aspects here, that measurement outcomes in a particular basis will correspond to orthogonal vectors. So say you're flipping a coin, you have two outcomes, heads and tails. Go ahead and make a picture here. Our Hilbert space will be two-dimensional. Let's say that this is tails, and this is heads. And they're perpendicular because when you flip a coin, they're mutually exclusive outcomes, heads or tails. And the quantum state could be anywhere in this two-dimensional Hilbert space. And so if I put a theta there, I can write the general form of my psi as psi is equal, well, it's not completely general, but it's pretty general. Cosine theta t plus sine, let me back that up, plus sine theta h. So that's a representation of that vector. We'll go into later what the more general one is. If I need to stick a little EI gamma, that's the most general one, but we'll come back to that later. But again, the point is, if you have mutual exclusive outcomes, then those correspond to orthogonal directions, essentially. And we kind of say this in a simplistic way, that each dimension of the Hilbert space corresponds to a possible measurement outcome in some basis. You choose your basis, those dimensions correspond to outcomes. And this is for simple cases. We won't get into any more complex scenarios for that. So all this was with talking about a single quantum object, the Ket vector representation, or the Bra-Ket formalism, if you will, and restating our postulate 1, the quantum state. We could slightly change this again, but this is pretty much the full definition, a proper definition of our first postulate.